Today, we are going to go back to calculus. So calculus, we all know, is a very interesting section, and it's probably the favorite of all those who love mathematics. So which chapter are we looking at today? We're going to look at methods of differentiation. So methods of differentiation is a second chapter which follows limits, continuity, and differentiability. Towards the end of differentiability, we look at the first principles using which we define the derivatives of a lot of functions. This chapter kickstarts from there and then goes into the details of differentiation. So we look at the standard formulae for the derivatives of a number of functions, which sometimes we would have derived using first principles. Sometimes we just accept it. If you're all interested, you can definitely derive them using first principles and see for yourself. So in this video, I am going to analyze this chapter for you from the JEE examination point of view, quickly take you through some concepts before the all-important question solving session. So how important is this chapter from the examination point of view? Well, to be very honest, this is one of the least important chapters when it comes to direct questions, because direct questions hardly ever come from this chapter in the advanced examination. Well, from 2013 until 2018, there has been only 1 year in 2016 when a direct differentiation question came in the examination. But does this make this chapter any less important? On the contrary, this is a very, very important chapter because this chapter is the foundation for application of differentiations or application of derivatives. Application of derivatives is one of the most important chapters in calculus. Every year, 1 or 2 questions definitely come from there. And without understanding differentiation, you can definitely not understand application of differentiation or application of derivatives. So this chapter is the crux of differentiation, and you have to definitely understand this chapter very well. So what about the types of questions which come from here? Well, I've told you in 2016 one question came from this chapter. It was a very simple question. They had defined two functions f and g, and then they had asked us to do a little bit of manipulation with the derivatives. But what about the type of question? It was a multiple correct answer kind of question, and it was a very long question. So this is the trick with the differentiation. Though the questions are very easy, a key point that you must remember is that these questions will be very long. So attempt these questions only if you have enough time in your kitty, because if you don't have enough time, this question is going to eat up a lot of your time. So solve all the other easy questions which you're sure to solve, and only then come and solve the differentiation question. Of course, in the main examination, every year one question comes from this chapter, and the different topics are tested in different years. But in the advanced examination, I would bet that not many questions will come from this chapter directly. But of course, this chapter is important, so let's quickly look at all the concepts that are there in this chapter. So we begin the chapter on differentiation by definitely introducing you to a number of standard differentiation results. We introduce the formulae by teaching you the first principles and deriving them, and then we list down all these formulae. So knowing all these formulae is going to be very important. Of course, we're not asking you to mug them up, but if you solve n number of questions, then you will be able to say that the differential of sin x is cos x and the differential of cos x is minus sin x, even without deriving them using the first principles. So this is how we begin the chapter. We look at all the different formulae involved in differentiation. Then we move on to some differentiation theorems. We look at the algebra of differentiation and all these things before moving on to the very important chain rule of differentiation. Now, chain rule of differentiation makes the difference between understanding differentiation and not understanding differentiation. The nitty-gritty tiny details are where chain rule questions can sometimes go completely wrong. Following chain rule of differentiation, we look at implicit differentiation. So we start the chapter by looking at y is equal to f of x, and then we differentiate y with respect to x. So we only have to take care of one variable when we are differentiating, but then we move into further complex concepts and look at what is implicit differentiation. Following implicit differentiation, we look at one more interesting concept, which is going to be parametric differentiation. So we will express a function in terms of a parameter. So instead of saying f of x, we will say f of x of t and f of y of t. So we will express x and y's in terms of a different parameter, and then we will introduce the concept of implicit differentiation there. We will introduce the concept of chain rule there and make the problems really peppy and interesting. So following parametric differentiation, we will also look at logarithmic differentiation. Logarithmic differentiation is very interesting because a lot of results which otherwise are difficult to prove can be proved very easily using logarithmic differentiation. So all these are different rules that help you solve differentiation questions. All first order differentiation is what we see using all these different tricks and rules. Before concluding the chapter, we look at higher order differentials. We look at how to compute the second order differential, how to compute the third order differential, and so on. So in fact, no concept is very new once you understand the concepts of basic differentiation. So initial parts of differentiation where you know the formulae, and then chain rule of differentiation, and maybe a little bit of implicit and parametric is all that is needed to understand the chapter. The rest of the topics such as logarithmic differentiation or higher order differentiation is just a direct consequence of whatever you've learned in the first part of this chapter. So this chapter is not at all difficult. It's a very easy chapter, but again, I will keep insisting this as we solve questions, that in this chapter you have to pay a lot of attention to each and every detail, because details define this chapter, and it is the details that is going to be the difference between getting a question correct and going wrong in this the questions from this chapter. So let's have a quick look at some very interesting questions from this chapter, and I will show you how much the details are important in this particular chapter. So in this question, we've been given a definition of fn minus 1 of x as log of fn of x, where n is any natural number. Further, we've been told that f naught of x is equal to x minus 1. The objective of this question is to find out the derivative of fn of x with respect to x. So in order to solve this question, let's first make use of the data that is given to us. We know that this is a multiple correct answer kind of question, so there might be more than one correct answer. And remember, there are partial marks for each correct answer, so even getting one correct answer right is a big deal because we get some marks. Of course, our aim is to get everything correct. So let's start by looking at whatever is given to us. So we've been given that fn minus 1 of x is fn of x, in fact the log of fn of x. So I'm going to take the derivative of fn minus 1 of x with respect to x. So what is the derivative of fn minus 1 of x? It's going to be 1 divided by fn of x. But remember to use the chain rule of differentiation, because now you have to differentiate fn of x. So it multiplied by the derivative of fn of x. Okay, so this is what is the derivative of fn minus 1 of x. Now, if I cross multiply this fn of x onto the other side, I get the derivative of fn of x, which is what has been asked in this question. So I get the derivative of fn of x as the derivative of fn minus 1 of x multiplied by fn of x. So one of the options, in fact option D, says that the derivative of fn of x is equal to fn of x multiplied by the derivative of fn minus 1 of x. So this is one of the correct answers to this question. Very easily we have got one correct answer to this question, but that's not it. We have to manipulate this and arrive at probably more than one answer. So let's see if we can manipulate further. So if the derivative of fn of x is fn of x multiplied by the derivative of fn minus 1 of x, I can write the derivative of fn minus 1 of x as fn minus 1 of x multiplied by the derivative of fn minus 2 of x. What did I do in the expression for the derivative of fn of x? I replaced n with n minus 1, and everywhere I did the same thing. I replaced n with n minus 1 and I got an expression for the derivative of fn minus 1 of x in terms of fn minus 1 of x and derivative of fn minus 2 of x. I'm going to continue doing this. So you see the pattern here. I will get the derivative of fn minus 2 of x as fn minus 2 into derivative of fn minus 3 of x, correct? So what I will do is I am going to take derivative of fn of x, and that is equal to fn of x into the derivative of fn minus 1 of x, which is nothing but fn minus 1 of x, into the derivative of fn minus 2 of x. Now the derivative of fn minus 2 of x is fn minus 2 of x into the derivative of fn minus 3 of x. This is going to go on until finally you will have f1 of x multiplied by the derivative of f0 of x. Correct? Now this term is going to be the derivative of f1 of x. The derivative of f1 of x will be f1 of x multiplied by the derivative of f0 of x. So this is going to be the expression for the derivative of fn of x. Now what is f0 of x? So f0 of x is nothing but x minus 1, and I can easily differentiate it to get the derivative of f0 of x to be equal to just 1. So now the derivative of fn of x is nothing but fn of x into fn minus 1 of x, so on until f1 of x. Don't you see this in one of the options? Of course you do. This has been given in option B. So option B is yet another correct answer to this multiple correct answer kind of question. We got one option correct very immediately, but in order to get the other option correct, we had to struggle a little bit, but of course not a lot of manipulations. So we have arrived at the answer. This is the thing with questions from methods of differentiation, because this chapter is a very easy chapter. The questions which come in the advanced examination generally tend to be twisted and pretty lengthy. So be ready to solve some lengthy questions when it comes from methods of differentiation. Let's look at yet another question. This is a parametric differentiation kind of question. Here we've been given the values of x and y in terms of a parameter t. We've been told that x is equal to log of mod 2t and y equal to the mod of tan inverse of mod t, and this parameter t has been told to be a negative number. The objective is to find out the value of this funny looking expression. So let's try and solve this question. Being a parametric type of question, we'll have to differentiate both x and y in terms of the parameter and then divide them to get dy by dx and so on. You see in this question, we need to find out d square y by dx square. So it's a higher order differentiation type of question. So let's get into the nitty-gritty details of how to solve this question. Now, since x and y have modulus inside them, in order to differentiate them, let's try and get rid of that mod, because it's difficult to differentiate with the mod sign on. So how do you take away the mod sign? You've been told that x is log of mod 2t, and what is t? T is a negative number, so mod of 2t will be minus 2t. So x is nothing but log of minus 2t. Now that was very simple. What about y? Now y has double mod. Y is mod of tan inverse of mod t. So what is tan inverse of mod t? Well, t is a negative number, so tan inverse of mod t will be nothing but tan inverse of minus t, correct? It's going to be tan inverse of minus t. Now what is mod of tan inverse of minus t? Remember, tan inverse of minus t, because minus t is a positive number now, tan inverse of minus t is going to be already positive. So the mod of tan inverse of minus t is going to be simply tan inverse of minus t. So that extra mod which is there, that is superfluous. So y is tan inverse of minus t, which is nothing but minus tan inverse of t. Now, this is a point where a lot of students can commit a mistake, because they will write y is equal to the mod of tan inverse of minus t and then simplify tan inverse of minus t as y equal to the mod of minus tan inverse of t. Then because there is a mod and there is a minus, you have the tendency of writing y as tan inverse of t. Now this is wrong. Why is it wrong? Because tan inverse of t is already a negative quantity. Because t is negative, tan inverse of t will be negative. So with the minus, minus tan inverse of t will be a positive quantity. So that second modulus which is there, that is superfluous, and that has to be just removed without changing anything. If you remove the minus from outside the tan inverse of t in this step, you're actually in trouble, because then you get the modulus of something as a negative number, which is not possible. So y is minus tan inverse of t. Now let's differentiate. From here on, it's a simple differentiation question, very routine parametric differentiation question. What is dx upon dt? Well, dx upon dt is very simple. You have to differentiate log of minus 2t, which is 1 upon minus 2t into negative 2. This is the chain rule of differentiation, and you get the value of dx upon dt to be equal to 1 upon t. Now, what is dy upon dt? Well, dy upon dt, again, very straightforward, minus 1 upon 1 plus t square. And from here, we get the value of dy by dx as dy by dt divided by dx upon dt. Don't do it the other way around. It is not dx upon dt divided by dy upon dt. It's the other way around, dy by dt upon dx by dt. So you get minus 1 upon 1 plus t square divided by 1 upon t, which gives me negative t divided by 1 plus t square. That's the value of dy by dx. Now let's differentiate it again with respect to x to get the value of d square y by dx square. Now dy by dx is a quotient of two expressions, so d square y by dx square, in order to find that, we're going to use the quotient rule of differentiation. So quotient rule of differentiation, keep the denominator, that is 1 plus t square, differentiate the numerator. What's the numerator? It's minus t, so upon differentiating you get minus 1, but do not forget dt upon dx. Because now dy by dx is not in terms of x but in terms of t. So if you are differentiating dy by dx in terms of with respect to x, then you have to differentiate t with respect to x. Do not forget this. Another bit of information that a lot of students will forget, and they will commit blunders in this solution to this question. Minus, you keep the numerator now, the numerator is minus t, and differentiate the denominator, which is 1 plus t square, which will give you a 2t, and again, not to forget dt upon dx. This is all divided by the denominator square, 1 plus t square, the whole square. Now it's a matter of just simplifying. What is dt by dx? Well, we have seen the value of dx by dt to be 1 by t. So dt by dx is going to be t. I'm going to replace dt by dx here by t, and then let me take that t outside, t by 1 plus t square, the whole square. Let me take that whole thing outside. Then you see that there is a minus t square here and a plus 2t square here. So from that, you're going to get t square minus 1. So d square y by dx square is going to be t times t square minus 1 by 1 plus t square, the whole square. There is a reason why I'm leaving it at this, because if you look at the question, d square y by dx square is divided by t, so I am going to keep that common factor of t because they will cancel out and the simplification becomes very easy. So now let's head into the very complicated expression whose value we had to find out. Let's substitute for d square y by dx square as t times t square minus 1 by 1 plus t square, the whole square, and dy by dx, we know what is dy by dx, that is t minus t by 1 plus t square, and we have to whole square this thing. So now you will see that the t in the denominator and the t in the numerator will cancel out, and what you see is there is a 1 plus t square, the whole square, multiplying both these terms, which will cancel out with both the denominators, because both the denominators are 1 plus t square, the whole square. So now you are all left with the t square minus 1 minus of t square. That's all that you need to do. So you will be left with the t square minus 1 minus t square, but with the modulus sign. So the solution for this is mod of minus 1, which is 1. A very straightforward solution. At the end, we just got number 1 as the answer to this question. It's a very systematic approach that is needed to solve this question. Parametric differentiation questions tend to be pretty long if asked in the advanced examination because the concepts involved are very simple. There isn't any rocket science in this question. So generally MOD questions tend to be pretty long, and you have to be ready to systematically solve them without missing any of the intricate details. Now this is a very interesting question. We've been given a function which is from real numbers to real numbers, and this function satisfies this condition, which is the mod of f of x minus f of y is less than or equal to x minus y the whole cube. A g of x has been defined as f of negative x plus f of x. Okay, so the argument of f and g of x is negative x plus f of x. The objective is to find out the derivative of g of x at x equal to 1, or we have to find out what is g dash of 1. So where is derivatives in this question? We've been given a function. Its definition has not been given, but a condition that it satisfies has been given. So how do you arrive at derivatives? And that is where your understanding of the concept of differentiability is going to come into picture, because the condition that is given is f of x minus f of y all inside mod is less than or equal to x minus y inside mod the whole cube. What I'm going to do is I'm going to rewrite it in a way from where you can very easily identify derivatives. I'm going to rewrite this as mod of f of x minus f of y divided by the mod of x minus y less than or equal to the mod of x minus y the whole square. What I did is I brought one mod of x minus y to the denominator on the left hand side, and now a lot of you will start seeing a derivative. F of x minus f of y divided by x minus y. What is missing? A limit is missing. So we're going to take limit on both the sides. So I will take limit as x tends to y of the left hand side, which will be an entire mod now because there's a mod in the numerator and the denominator. The whole mod of f of x minus f of y divided by x minus y, that's going to be less than or equal to the limit of x tending to y of the mod of x minus y the whole square. Now you see the derivative, don't you? You definitely see the derivative here, because the left hand side now, whatever is inside the modulus with the limit will be f dash of x, because x is tending to y. So it can be, if you write x minus y tending to 0 and consider x minus y as this variable h, then you have the derivative there. A very, very beautiful way of expressing a derivative question. So what you have on the left hand side is actually mod of f dash of x and mod f dash of x less than or equal to limit x tending to y of x minus y the whole square. What is limit x tending to y of mod of x minus y the whole square? It's nothing but 0. So on the left hand side you have mod of dash of x less than or equal to 0. So now comes the analysis bit. So if mod of f dash of x is less than or equal to 0, this means that f dash of x has to be equal to 0, correct? Because mod can never be negative. Mod has to be always 0 or positive. So if mod of f dash of x is less than or equal to 0, this means that f dash of x equal to 0 for all real numbers x. An amazing result that we've just found out. F dash of x is a constant number, and that is equal to 0. We're going to make use of this fact when we're computing g dash of x. G of x has been defined as f of minus x plus f of x. So g dash of x is going to be equal to f dash of negative x plus f of x. And then don't forget the chain rule, which is going to be minus 1 plus f dash of x. Now, even those students who would have forgotten the chain rule will get this question correct from here on, because f dash of whatever is the argument, f dash of anything is equal to 0, correct? So g dash of x is also going to be equal to 0 for all real numbers x. And 1 is also a real number, so g dash of 1 is actually equal to 0. A fantastic question, because you couldn't see derivatives in the question statement, but we arrived at derivatives, and then we did some very nice analysis and finally arrived at this beautiful solution, g dash of 1 equal to 0. I hope you had a lot of fun solving this question. We will look at some more really nice questions. So in this question, we've been given a function f of x, which is sine of cos inverse of 1 minus 2 to the power 2x divided by 1 plus 2 to the power 2x. Further, it has been told that f dash of 1 is minus b over a log 2. It's b and a that we are interested in, because the objective of this question is to find out the value of magnitude of 4b minus 2a, the modulus of 4b minus 2a. It's a very fancy way of asking you to find out what is the value of a and what is the value of b. It's an integer type of question. So let's try and solve this question in a very systematic way. First of all, there are trigonometric and inverse trigonometric functions in the definition of f of x. Let's try and simplify that, because if I directly get into differentiating this, it's going to lead me into a lot of trouble, because I'll have to use the chain rule of differentiation multiple times and a lot of unwanted terms will appear and simplifying them will become difficult for me. So let's try and simplify that. So cos inverse of 1 minus 2 to the power 2x divided by 1 plus 2 to the power 2x. What if I call 2 to the power x as some dummy variable t? If I say t equal to 2 to the power x, then what happens to this term here? Well, this term here becomes 1 minus t square divided by 1 plus t square, isn't it? Cos inverse of 1 minus t square divided by 1 plus t square. Now that is nothing but sine inverse of 2t divided by 1 plus t square, and we are getting all these using the relation between half angles of tan and sine and cos and all these relations. So this was nothing but 2 times tan inverse of t. Correct? If you put the value of t to be equal to tan theta, you will see that 1 minus tan square theta by 1 plus tan square theta is cos 2 theta. So cos inverse of cos 2 theta is 2 theta. Which is nothing but 2 times tan inverse of tan theta, which is also 2 theta. So all these formula comes from the relation between half angles of sine, cos and tan. So this is the crucial bit of observation that you must make so that this problem becomes easy. So now f of x is nothing but sine inverse of 2t by 1 plus t square, which is nothing but 2t divided by 1 plus t square. And t is 2 to the power x, so this is 2 into 2 to the power x divided by 1 plus 2 to the power 2x. A little bit of detail here. You have to make sure that 2t by 1 plus t square is in the domain of sine inverse, and of course that will be taken care in the question definition itself, but this is a little bit of detail that is important when you're dealing with sine inverse functions. Okay, so f of x is 2 into 2 to the power x divided by 1 plus 2 to the power 2x, a very nice looking expression, and I am now going to differentiate this expression. So what is f dash of x? Well, I am going to use the quotient rule of differentiation. 1 plus 2 to the power 2x, the denominator as it is. Differentiate the numerator, 2 into 2 to the power x log of 2. Minus the numerator stays as it is, 2 into 2 to the power x, and differentiate the denominator, which is going to be 2 to the power 2x into log 2. Is that it? This is where you must not go wrong, because there is a small chain rule there, because it's 2 to the power 2x. You have to differentiate the 2x, which will give you an extra 2. And this is entirely divided by 1 plus 2 into 2 to the power x, the whole square. Okay, so that is your f dash of x. Substitute the value of x to be equal to 1. Substitute this value of x to be equal to 1, because f dash of 1 is minus b over a log 2. So wherever you see an x, you put the value of x equal to 1. So you will get the value of f dash of 1 to be equal to, well, there is a 1 plus 2 to the power 2x, that is nothing but 5. So 5 into 2 into 2 into log 2. Minus, well, whatever is the term there, you will get 2 into 2 into 2 to the power 2x, that is 4, into 2 into log 2, all divided by 1 plus 2 to the power 2x. 1 plus 2 to the power 2x is going to be 5. 5 square is 25. So now we're going to keep the log 2 common out, because in f dash of 1, well, f dash of 1 was nothing but minus b over a log 2. So I'm going to keep that log 2 common out. 5 into 2 into 2, that's going to give you a 20. 2 into 2 into 4 into 2 is going to give you a 32. 20 minus 32 is minus 12. And 5 square is 25. So I get the values of what a and b are very easily. A equal to 25, b equal to 12. The expression whose value we need to find out is mod of 4b minus 2a. 4b is 48, 2a is 50. Mod of minus 2, that's what 48 minus 50 is. Mod of minus 2, that's equal to 2. So correct answer to this integer type of question is 2. a rather interesting question. Well, I wouldn't call this a differentiation question. This is more of an inverse trigonometry question, because the crux of this question lies in that initial substitution, which will give you a very simplified expression to solve. Later on in life, it's just a little bit of quotient rule, a little bit of chain rule, and mathematical manipulation. I hope you had fun solving this question, and we will solve a few more questions. So in this question, we have a determinant. F of y has been defined as this determinant here. Now, if you look at the determinant, it has some a's and b's appearing. In fact, a1, a2, a3, and b1, b2, b3 are appearing. And what has been told about a1, a2, a3, b1, b2, b3 is the fact that these are all even numbers. Okay, these are all even integers. That has been told about a1, a2, a3, b1, b2, b3. The objective is to find out the value of f dash of 2. So that's a little bit of a trick, because how do you differentiate determinants? Well, this is how you differentiate a determinant. So if you have a 3 by 3 determinant, then the differential of that 3 by 3 determinant is going to be the sum of 3 determinants. Now, how do you take the sum of these 3 determinants? The first determinant, you are going to take the differential of the first row. The second determinant, differential of the second row. The third determinant will have the differential of the third row. The rest of the elements are going to remain the same in all these 3 determinants. So the differential of my function is going to be the sum of these 3 determinants, wherein in the first determinant I have taken, if you notice, the differentials of the first row elements. Remaining 2 rows are exactly the same as in the original determinant. In the second determinant, I've taken the differential of the second row elements, keeping the first and the third row elements exactly same as the original determinant. And in the third determinant, I've taken the differential of the third row elements. Now I have to find out the value of f dash of 2. So wherever there is a y, I am going to replace it with a 2. So if you notice, everywhere you have a 1 minus y. So 1 minus y is going to be 1 minus 2, which is equal to -1. Correct? So you have a -1 appearing there. Now let's look at the elements which are in green here. These are the elements that have not been changed, right? So you have a -1 raised to the power a into b, ai into bj, something, where I and j are 1, 2, and 3. What has been told about a's and b's? A's and b's are all even numbers. So this means their product is also even, and you have a -1 raised to even number, which means all my green elements are actually going to be ones. Correct? I'll have 1, 1, 1. So this will be equal to 1. This will be 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 1. So all my green elements are actually going to be 1. What about my yellow elements? So my yellow elements have a coefficient aibj. They are going to stay as aibj's with a minus sign there. And what is inside the bracket? A -1 raised to aibj minus 1. So aibj is even, aibj minus 1 will be odd. So I have -1 to the power odd, which means all the negatives are going to get cancelled out, and I will be left just with the coefficients. So my f dash of 2 is going to be the sum of these 3 determinants. No negative numbers anywhere. a1, b1, a1, b2, a1, b3, 1, 1, 1, 1, 1, 1, and similarly the other 2 determinants. Now we have to evaluate these determinants. Is it difficult to evaluate them? Not at all, because 2 rows of each of the elements are exactly the same. So this means that the value of the determinant equal to 0. So f dash of 2 will be equal to 0 plus 0 plus 0, which is a very, very fancy way of saying that f dash of 2 is actually equal to 0. So the correct answer to this question is f dash of 2 equal to 0. Well, this was not at all a complicated question. The only reason why I solved this question is to make you aware of the fact that determinants too can be differentiated, and you better know the formula for differentiating determinants, because sometimes questions do come from this section. So in this question, we've been given y, which is actually an infinite series sort of a question, but it's more than an infinite series, because there's an under root and a log and all these terms appearing here. And the objective is to differentiate this y and find out the value of the differential when we plug in x equal to 1. Well, it's a routine question. People who have seen and worked out problems from the chapter on differentiation know how to solve this question. But for the others who have not come across such questions, very quickly I'll take you through how to solve this question. So if you see what is inside the under root here, you actually have under root of log x plus 2 times under root of log x plus 2 times under root of log x, and this goes on up to infinity. So in fact, this term is actually y itself. So y is equal to under root of log x plus 2 times y itself. Correct? So this is how you're going to solve this question. Now I will take square on both sides to get y square equal to log x plus 2y. Correct? So now y square is log x plus 2y. I'm going to take the differential of this. So I'm going to use implicit differentiation. 2y y dash is 1 by x plus 2y dash. Now, what is the value of x? The value of x is equal to 1. So when x is equal to 1, what is the value of y? The value of y will be log 1 plus 2 times log 1 plus 2 times log 1 plus 2 times log 1 and so on until infinity. What is log 1? Log 1 is 0. So y is 0 plus 2 times 0 plus 2 times 0 plus 2 times 0. Of course, I think I forgot to mention the under root. So there's an under root everywhere, but it really does not matter because you're taking square roots of 0. So you have y equal to under root of 0 plus 2 times under root of 0 plus blah blah blah. So eventually you have the value of y to be equal to 0 when x equal to 1. Right? So this means that when x equal to 1, y equal to 0, my left hand side becomes 0, right hand side is 1 by 1 plus 2y dash. So y dash at x equal to 1 will be equal to negative half. That's the correct answer to this question. A very, very simple question. So now let's look at one more pretty simple question. So we've been told that x into e to the power xy minus y minus sine square x equal to 0. The objective is to find out what is the derivative of y with respect to x when x equal to 0. First and foremost, just like in the previous question, let me find out the value of y when x equal to 0. So I'm going to plug in the value of x is equal to 0 in this expression. Everywhere, wherever there is an x, I will plug in the value of 0. So I get 0 minus y minus sine square 0 equal to 0, which means y equal to 0. So when x equal to 0, I get the value of y equal to 0. So x equal to 0, y equal to 0. So now we're going to carry out implicit differentiation. Well, there is going to be a lot of nitty-gritty details of differentiation that you have to pay attention to in this question, because the first term has a product of two terms, so we're going to use the product rule. So x into e to the power xy, when upon differentiating I get e to the power xy plus x into the differential of e to the power xy. Differential of e to the power xy is e to the power xy, and then remember the chain rule of differentiation multiplied by the differential of xy. What is the differential of xy? We use the product rule. So you see a product, inside that a chain rule, inside that a product, and so then you get x into y dash plus y minus, well, the rest of the terms are not that complicated. A differential of y is y dash. Differential of sine square is 2 sine x into cos x, and all these is equal to 0. So plug in the value of x equal to 0, y equal to 0. In fact, if you notice, we never needed to find out the value of y, because the moment you put x is equal to 0, a lot of terms automatically vanish, right? Because when you put x is equal to 0, the product of xy will become 0. So you have e to the power 0, which is 1 plus 0. I'm not even interested in anything else. Minus y dash minus you have 2 sine 0 cos 0. 2 sine 0 cos 0, cos sine 0 being 0, cos 0 doesn't matter, so I get another 0 equal to 0. So my y dash is e to the power 0, which is 1. So the correct answer to this question is y dash equal to 1. So you might all be wondering as to why did I solve a couple of very simple questions toward the end of differentiation? Well, it is just to make sure that you understand differentiation chapter is all about paying attention to these nitty-gritty details. You saw this last question, it had a product rule and then a chain rule inside the product rule, and in that chain rule there was a product rule. So differentiation is all about paying attention to all these nitty-gritty details. Again, questions are never ever difficult from this chapter. They only tend to be very long. But more often than not, I have seen that students commit a lot of silly mistakes in these chapters because they forget paying attention to all these tiny things which will result in blunders in the examination, because these are multiple correct answer kind of questions or multiple choice questions which have one correct answer. So even if one sign is wrong, you get a completely wrong answer, and unlike in your board examinations, you will not be given partial marks for steps. So make sure that if an MOD question, a methods of differentiation question comes, you actually solve it rigorously by paying a lot of attention to detail. All the time that you've saved from questions from other chapter, that time has to be invested in a question of this kind, which is going to be very easy but really time consuming and will test your focus and your concentration and how much of attention you can pay to each of the small things that is there in the question. I hope you will have a lot of fun practicing questions from methods of differentiation. Not a difficult chapter, but a really challenging chapter. So make sure that you solve nice amount of questions from this chapter, and stay tuned because I'm going to very quickly come back with yet another very interesting chapter and its analysis.
For more videos and live lectures on the JEE, click on the subscribe button now.